In this related rates problem, we have a man that walks along a straight path at a speed of 4 feet per second. There's a searchlight located on the ground 20 feet from the path and is kept focused on the man. And we want to know at what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight. All right, there's a couple things we want to make sure we understand on the diagram on this one before we move forward. First off, let's place this 20 feet. You'll recall that anytime we're measuring from a point, and we'll consider this light being a point to a line, we're always measuring along the shortest distance, and the shortest distance makes a perpendicular with the line, and so that's the 20 feet right there. And we are asked here at the end, at what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? That's this point. This is the point closest to the light. All right, so let's go back and get this other information in here. We've got this man, he's walking along this path at a speed of 4 feet per second, and somehow we have to mark his position. And we're going to mark his position with respect to that point we were talking about before. So this distance here is going to be x. So we can see that his speed is the rate at which x is changing. So we would say that dx dt equals 4 feet per second. Only we need to take a look at what's happening to x. As the man gets closer and closer to this point, x is actually decreasing. Therefore, it's going to be a negative 4 feet per second because x is decreasing, and that is how it's changing. Now then, the next thing I'm asked about is finding the rate at which the searchlight is rotating. Now, rotating implies an angle. I don't like how that looks. Okay, so rotating implies we have to work with an angle. So let's finish out our triangle here so that we have an angle. And here's the angle at which that searchlight is rotating. So you can imagine it's shining on him here, and as he moves along, we've got this line here. The hypotenuse keeps moving. All right, so now we've got, and we need to mark what we want to find. So it says at what rate is the searchlight rotating? We want to find d theta dt when, and it asks us when the man is 15 feet from that point. So that's going to be that measure of x when x equals 15. All right, so we have here a triangle. We have theta and x, and we need some relationship that meets them. And we have one other constant. This 20 feet is always 20 feet. So you should be thinking, I've got a right triangle. I know two sides. I'm dealing with an angle. And we wanted to use some trigonometry here. You'll notice that x is my opposite side. 20 is my adjacent side. So it would make sense to use this equation, that the tangent of theta equals opposite x over adjacent 20. All right, these are the very variables that were given to me, so I don't need to make any adjustments before I take the derivative. So you recall that the derivative of tangent is secant squared, or 1 over cosine squared is really helpful in this situation, so I'm going to use that one. So 1 over cosine squared times the derivative of theta, which is d theta dt, which is what we want to find, equals, now x over 20, I have a lot of students who struggle with that. Think of x over 20 as the same thing as 1/20th x. So that's going to equal the derivative of 1/20th x is 1 over 20 times dx dt. All right, we needed to find d theta dt, and I can actually solve for d theta dt by simply multiplying by cosine squared. That's one of the reasons I chose to use this instead of secant squared. So I have 1 over 20 times dx dt times cosine squared theta. All right, so now I'm just ready to plug in my numbers. I've got 1 over 20. I know that dx dt is negative 4, and I need to figure out cosine of theta. All right, now I got to look at my clues to figure that out. So you'll recall we were doing this when x equaled 15. So let's just draw that special triangle. I don't want to put it on my diagram because x is not always 15. It was just 15 for this brief time. So we've got a situation where this is 20, and this is 15, and I know I just need to use, and I've got theta here, and I want the cosine, so I need adjacent over hypotenuse. I'm going to need that hypotenuse, so little Pythagorean theorem, and I'll know my hypotenuse. I've got 225 and 400. That gives me 625 equal to c squared, which means that c is 25. So that means that the cosine of theta is going to be adjacent, which is 20, over hypotenuse, which is 25, which reduces to 4/5. So I'm going to come back over here, and I'll put in 4/5 for the cosine of theta, and I need to square that. So we have d theta dt equal to, and let's just simplify this, negative 1/5 is negative 4 over 20 times 16 over 25. And one more round, negative 16 over 125. If you want a decimal, of course, you can use your calculator. Let's get units on this. How are we going to measure theta? We're going to measure theta in radians. And time we measured, let's look at the original problem. Up here, time was in seconds, because we can see that he was moving at 5 feet per second. So this is going to be radians per second.